I'm writing this for the horizontal motion that we have. And I've got to supply what goes in the box there. So Tx minus friction. So you see the difference, we actually have something over here. We have a net amount. I only get that if tension X is bigger than friction. Okay? Luckily they tell us friction is 320 newtons just like before. Okay, so I'll have to do a little bit of math to this. So again, this is Newton's second law. It looks so simple, right? It's just F is equal to ma, that's it. What makes it difficult is you have to supply everything that goes in that dotted box. Using a free body diagram hopefully makes that a lot easier though. Okay, so then from here, I'll have to do a little bit of algebra, add friction to both sides. So ma plus friction is Tx. Okay, and I know this. Again, I'll just have to figure out what the acceleration is. And this is the part that should be kind of a review, because we did it last week or so. Yeah, I'll do it like this. Final velocity minus initial velocity divided by time. So we go up to 12 meters per second, starting at rest, and I think this happened in 10 seconds. Yep, okay. So you get 1.2 meters per second squared. So that's what the acceleration is. And now you can take this and put it in here for the acceleration. Okay, because you know the mass, here's the acceleration, friction's given. That will give you T in the X direction. Just like before we solved for tension in the X direction, you'll have to do a little bit more work to get the overall tension though. So this is to get Tx. Same thing, if you know Tx, you know this angle, you can get the overall tension then. Okay? All right, good. Excellent. Any questions on this one? Okay, very nice. Here's a little bit of a new take on the one that we did previously as well. Here's the block accelerating upward now. So we did a similar one where it was just hanging or going at a constant speed, but now it's accelerating upward at 5 meters per second squared. So we actually have a net force in this problem, right? I say we have a net force because we have an acceleration. All right, let's put this one on paper as well. Okay, so mass, 100 kilograms, the weight, 980 newtons, acceleration of 5 meters per second squared. And find the tension. Now when you read through this chapter, you're not going to find anything called the tension formula. There's nothing called the tension formula. We have to realize that we have forces, acceleration. What we have is Newton's second law, and hopefully the tension that we're looking for will come out in Newton's second law. Here's the picture. Tension, weight. I purposely drew the tension larger to illustrate that we actually have a net force that's up then. Okay, so if this were the test and I just did this, I'd probably give you at least a couple of points for that. You add in the free body diagram, now we're probably up to like 4 or 5 out of 10. We're really organizing the problem. And then once we write Newton's second law down, just this part of it, I would say you're up to like 6 points, right? Now we got to put the details in. So I'm writing tension minus weight. I'm trying to figure out tension. It's in Newton's second law, the part that I have over here, and then I can solve for the tension. So I'll have to add weight to both sides to give myself the tension. Okay, so 100 kilograms it was? Yep. Times 5 meters per second squared plus the weight, which is given as 980 newtons. So 1480 newtons. So the larger and larger the tension, the bigger and bigger the net force, the bigger and bigger the acceleration will be. Okay, good. So how did I know to even do this? Well, it's a problem involving forces, acceleration. So whenever you see that, immediately think, it's a Newton's second law problem. It's forces, acceleration. I know Newton's second law. I can, with the help of my free body diagram, start with this part, and then it's up to you to put whatever goes in the box. Okay, and again, that's what makes it tricky, right? It's only 3 variables, but the box part makes it hard. Okay, any questions on that one? All right. So here's another example that you can't see yet. We have a ball weighs 50 newtons, so that's the weight, pulled back by a rope at an angle of 20 degrees, just like the picture has. What is the tension in the pulling rope? So there's 2 ropes. It's hanging by one rope. There's a tension in another rope. We want to figure out what's the tension in the pulling rope. Okay? So let's draw this one out. So this is the tension we're trying to figure out. Here's the weight. This is 20 degrees. This is the tension that we want. There's actually a tension in this part too, right? I'll just call this one T1 and this one T2. And we're trying to figure out T2 in this problem. There's 2 different ropes. That's why I've got them both listed. And the weight of this is 50 newtons. And again, we're trying to figure out T2. All right, good. Excellent. So one thing to realize is nothing's moving at this point. So whatever force we have up is equal to whatever force we have down. Whatever's to the left has to be equal to whatever's to the right. So this is just up and down. That's nice. This one is just left or right. Turns out this is left, this is down. This T1 has a part in the x direction. So I'm going to call that T1x. And then it has a part in the y direction, so T1y. So from this picture, right now you already know how much T1y is. Right? So whatever forces are down have to be equal to whatever forces are up. So if you've got 50 newtons down, you also have to have 50 newtons up. Okay? Because all the forces are balanced on this ball. Okay, so we're getting somewhere. We really want to know what T2 is, though. What does T2 have to be equal to from my picture? What variable? I don't know how much yet, but it's equal to something written in the picture. T1x, excellent, because all the horizontal forces are balanced. Good, so this is perfect. So if there was a way to get T1x, I'm in business, right, because that's equal to T2. Luckily, I've got this angle. I've got a side, so I can get the other sides. So it looks to me like the tangent will work for us here. The tangent of 20 degrees is the opposite side over the adjacent side. So with a little bit of trig, I can come up with T1x. This is purely a trig thing here. This is the physics part here, right? Balancing the forces. Good, so once I get this, I know it's got to be T2. So 50 newtons, tangent of 20 is T1x. Okay, good, I'm still in degree mode. So 50 times tangent of 20. About 18.2 or something like that. All right, perfect. Excellent. All right, any questions on this one? All right, very good. Let's see where we're at here. Getting kind of low on time. Okay, so we just have a little bit to finish in chapter 5. Just a couple of other problems I wanted to go over. So definitely this weekend, take a look at this homework set and get most of them done. Any questions, email me. I think the first thing we'll do on Monday, when we actually meet again, is we'll go over any other parts of the homework. I might have to fill in a little bit of detail, but not too much. So finish up the homework, and then we'll go over the practice test as well. So tomorrow, look for that video on the next lab too. I'll let you know when it's up. You don't have to immediately do it. You have a whole week to do it or so. Okay, any questions on anything? Can you believe it's the end of week 4 already? So after next week, I mean, we still have to do next week, but after next week, the semester's like a third over, approximately. So we're in college time now, right? Everything goes faster, it seems like. Any questions? No? Okay. Well, have a good rest of the night. Email me any questions, and we'll actually see each other in person on Monday, hopefully. Okay.